Anyways, today we're gonna talk about Nusselt's number and how we can derive an explanation for why um the shorter the flow, the higher the heat transfer, and then we're gonna explain why a certain direction is gonna maximize that heat transfer. So first gonna write out the Nusselt number. So number, let's just see. Is equal to 0.332, and then Reynolds number, and then Prandtl number. And then so we know Nusselt numbers is equal to um H over L divided by K. So H is thermal, is the heat transfer coefficient. And then K is the thermal conductivity. And then L is just for length. And then we have this. And then now we can write out a Reynolds number. Okay, so Reynolds number is density, like Reynolds derivation, density times um velocity times length divided by viscosity, and then to the power of half, and then Prandtl's number. And then so we know, so now let's rearrange the equation. So we're gonna move L and K over to the other side. So we have um 0.332 K equal to um PV over U. Times, let's keep this in a bracket, and then square root of it, and then we move L out, so we have 1/2, and then Prandtl's number 1/3. And so we know that thermal heat transfer coefficient. We also move L over to the SI. I forgot. So L, so we would have 0.233 times K times P rho V U mu 1/2, and then L to the negative 1/2, and then Prandtl's 1/3. And then so now when we look at heat transfer coefficient and the length of the flow, you see that um they are inversely proportionate. So the higher, the greater the length, the lower the heat transfer coefficient. So greater the length, lower the heat coefficient. And so now we're gonna draw the boundary layer for the flow, and we can observe its phenomenon. Okay. So we see that boundary layer gets thickened as the length progress. So thicken, thicken, thicken. The reason why the boundary layers get thickened over the length is because at the wall, there's frictions, and then the property of viscosity causes it to slow velocity to go to zero, which would drag the fluid above it, and then that fluid would drag the fluid ahead of it, which create a thicker boundary layer as the length go by. And then now we're gonna draw. So now that we know that we established this and we know this, let's do this. So when we draw a plane right here, and let's say they have length L, and then length, another length L long, and then length L short. So we know that heat that the coefficient therm heat transfer coefficient measure how strong or how fast the how much the heat transfer is able to go through a la a layer, or how much heat flux go through a layer for convection. So we know that for the length to be the shortest, it has to flow in a normal direction, instead of like parallel, or any direction at any angle, because that would be significantly longer than the no in the normal direction. So heat flows heat flows more and most when it travels through a normal direction. Thank you for listening. Also want to add to some detail from an explanation that so you see that for this one up here, as the shorter the length of the flow, the thinner the boundary layer, which the thinner it is, which leads to less resistance. So um l- shorter L, thinner boundary layer, and higher heat transfer. And then so for over here, in the normal direction, the temperature gradient is the steepest. And heat flux depends on the difference or the temperature gradients. So the higher the gradients, the more the heat flows. So that's why heat flows in normal directions is always the greatest. Thank you for listening.